All right, let's dive into something that's a huge leap forward in computer vision. You probably remember Meta's original Segment Anything model, right? The one that could find basically any object in a photo. Well, now we've got its successor, SAM-2, and it's taking that same incredible power and unleashing it on the much wilder world of video.
You know, the original SAM was a total game changer for static images. You could click on a picture and boom, it would perfectly outline an object. But video is a completely different beast. It's fluid, it's messy, it's constantly changing. So the big question is, how on earth do you teach an AI to follow and segment an object that's always in motion?
So this jump from images to video isn't just a small step. It introduces a whole new world of problems. With an image, you've got a single, usually high-quality, stable snapshot. But in a video, objects are moving, they're changing shape, they're getting hidden behind other things and then popping back out. On top of that, the video frames themselves can be blurry or have a lower resolution. These are not small hurdles. They're fundamental challenges that needed a totally new way of thinking.
And that new way of thinking is SAM-2. Now, what's really cool here is that it's not just a video model. It's a unified model built from the ground up to understand both images and videos. And it does this by very cleverly just treating a single image as a one-frame video.
To really tackle this, the research team actually defined a whole new task they call Promptable Visual Segmentation, or PVS for short. The idea is so simple but so powerful. You should be able to click on any frame in a video, point to an object, and the model should then be able to track and predict its location across the entire video. That complete video mask, the object's path through time and space, is what they've dubbed a masklet.
The success of this whole project really comes down to three huge innovations. First, this new task, PVS, that we just talked about. Second, a brand new model, SAM-2, with this really unique memory-based architecture. And third, a massive, and I mean massive, new dataset called SAV to teach it. So let's break all of these down, starting with the model itself.
Okay, so the secret sauce behind SAM-2's ability to handle video is its streaming architecture. It's built to process a video just like you and I would watch it, one frame at a time. But the real key here is that it remembers what it's already seen.
You can think of this streaming memory architecture as the model's short-term memory. As each new frame comes in, the model doesn't just look at that one frame by itself. It actually looks back into its memory of the previous frames to understand the context, the motion, and to make sure it's still tracking the same object. This is what allows it to be both incredibly accurate and fast enough to run in real time.
The process for every single frame is this really clean four-step loop. So, first up, an encoder takes the current frame and breaks it down into a set of features. Second, and this is the really critical part, the memory attention module compares those new features to its memory bank of past frames. It's basically asking itself, okay, based on everything I've seen before, where is that object now? Third, the decoder uses all that context to predict the mask for the current frame. And finally, it updates its memory with this new info, getting ready for the next frame. It's a constant cycle.
And if we dive a little deeper into these components, you can see just how clever this whole system is. The memory bank isn't just a random pile of old frames. It's a structured queue that prioritizes the most recent frames and, importantly, any frame a user clicked on. Then you have object pointers, which act like a little mental tag for the object. And there's a brand new component called the occlusion head, which is smart enough to predict when the object is completely hidden, so it doesn't get confused and start tracking the wrong thing.
So how does it learn to do all of this? Well, it's trained on both images and videos at the same time. But what's crucial is that the training process actually simulates a user interactively clicking to correct mistakes. This doesn't just teach the model how to track an object. It teaches it how to listen and refine its predictions based on human feedback, which is absolutely key for making it work well in the real world.
Of course, a model this powerful needs an incredible amount of fuel. And in the world of AI, that fuel is data. The team had to build a gigantic, high-quality video segmentation dataset from scratch. And honestly, the way they did it was nothing short of genius.
They created what they call a data engine that worked in 3 phases. Phase 1 was just pure manual labor, using the original SAM on every single frame. Super slow. In Phase 2, they got a bit smarter and brought in an early version of SAM-2 to help automatically spread the masks from one frame to the next, which definitely sped things up. But Phase 3, that's where the magic happened. They put the full interactive SAM-2 into the loop, allowing annotators to just provide a few simple clicks here and there to correct the model's mistakes. And the efficiency gains were just staggering. The average time to annotate a single frame dropped from almost 38 seconds in the beginning all the way down to just 4.5 seconds in Phase 3. This created this perfect virtuous cycle. The better the model got, the faster they could create data, which in turn made the model even better.
What did that all add up to? A final speedup of over 8 times. That's right, using the fully mature SAM-2 model in the annotation process made the whole thing 8.4 times faster than when they started. This incredible efficiency is what allowed them to create the Segment Anything Video Dataset, or SAV, and it contains a mind-boggling 35.5 million individual masks. Now, to put that number into perspective for you, the SAV dataset has 53 times more masks than the next largest video segmentation dataset that exists today. It's not just a step up, it's a complete quantum leap for the entire research community.
Okay, so we have a super sophisticated model and a ridiculously massive dataset. But does it actually, work? Let's get to the good part and look at the results.
In tests, where you're trying to get a perfect mask with the least amount of effort, SAM-2 just blows the competition out of the water. When you compare it to other strong methods, which combine the original SAM with other state-of-the-art video trackers, SAM-2 achieves way higher accuracy.
But here's the real kicker. It gets that better result with more than 3 times fewer clicks from the user. I mean, think about that. Less work for a better result. That is a huge deal for any practical application, like video editing.
And this isn't just about interactive tasks. In the standard benchmark for video object segmentation, where you just give it a prompt on the very first frame and let it run, SAM-2 consistently beats other top methods. And it's not just in one category. It wins across every single prompt type, from a single click to a bounding box to a perfect mask. The performance gap is really significant.
But here's what might be the most remarkable result of all. Something you totally wouldn't expect. The team found that SAM-2, this new model designed from the ground up for video, is actually better than the original SAM at segmenting plain old static images.
And we're not just talking a little bit better. It's more accurate while also being, get this, 6 times faster. That is just a massive win in both performance and efficiency, and it's all thanks to its smarter, more effective architecture.
Let's just look at the hard numbers. Even when it's trained on the exact same image data, SAM-2 is already more accurate than the original. But when you add all that video data into its training mix, its performance on images jumps up significantly. It turns out that teaching an AI to understand motion actually makes it better at understanding a still life.
The research team really put it best themselves. They see SAM-2 not as just another small improvement, but as a genuine milestone for the entire field of visual perception. It's a new foundation that future research and countless new applications are going to be built on.
So what does all this really mean? It means we now have a tool that can understand and isolate objects in our dynamic, messy, moving world. From next-generation video editing and special effects to smarter robotics and augmented reality, the possibilities are just starting to open up. And that leaves us with the only real question left. What are we gonna build with it?